working through chapter summaries for matter and interactions. I'm on chapter 9, so this textbook, my favorite. Hope you like it too. Okay, let's just get started. Chapter 9, we start off thinking about energy for more complicated systems. So imagine that I have the following system. I have just two masses, and maybe they're connected by a spring. It doesn't really matter. And both of them are moving. The first thing I want to do is to calculate the center mass. So if this is mass 1, M1, and this is M2, I can find the vector position of mass 1, R1, the vector position of mass 2, R2, and then the vector location of the center of mass, RCM, is going to be equal to M1, R1, plus M2, R2, divided by the total mass, M1 plus M2. And that's how we define the center of mass. And that's for two masses, but the same thing works for 3 or 4 or infinite a number of masses, so it's not that big of a deal. And so that would be somewhere over here, just like that. Now, what if both of these things are moving? Let's say that one has a velocity v1, that has a velocity v2. It doesn't really matter at this point. Well, what's the velocity of the center of mass? Well, here's the trick. I can take the derivative of this. I can say v center of mass is equal to the derivative of r center of mass with respect to time. But that means I can just take the derivative of this. So I have over here m1 plus m2, 1 over that is a constant. And so if I take the derivative of something with a constant, I can just leave that out front. So I'm going to leave 1 over m1 plus m2. And now I have to take the derivative of m1 r1. Well, m1's a constant, so it's just going to be m1 dr1 dt. And that one too, plus m2 dr2 dt. Well, dr1 dt is v1. dr2 dt is v2. So this says the velocity of the center of mass is equal to m1 v1 plus m2 v2 over the total mass. But I can do something else. What if I multiply both sides by the total mass, which I'll call m? I get m v center mass is equal to m1 v1 plus m2 v2. So this is p total. That's the total momentum. That's the total momentum. So if I know the center mass and the center mass velocity, I can treat that object, in this case it's just two masses, I can treat the velocity of the center mass and the mass, total mass, as the momentum, the total momentum. That's kind of a big deal, right? Because then if I have a force acting on my system, I know the change in momentum of the center of mass. It's kind of important. In terms of energy, we can also look at the velocity relative to the center mass. And with that, we can write the kinetic energy as let's just write it as K. They call it translational, let's just say T, plus K rel. So this is the kinetic energy of the center of mass plus the kinetic energy relative to the center mass. Because now if I have that center mass moving, if these are moving towards or away, that may not change the total momentum, but it has energy, right? Because they're not going to cancel in terms of energy, because energy is always positive. Kinetic energy is always positive. And this relative kinetic energy, we actually can break into two kinds, vibrational and rotational. And the vibrational, I'll show you an image of this, animation of this in just a second. The vibrational would be motion towards or away from the center mass, and the rotational is motion perpendicular to the center mass, so it'd be rotating. Okay, I think let's go ahead and jump over and look at a couple of programs in Python. These are programs that come with the book, and so I think it'd be useful to talk about them. So I'm switching over to Python. I'll include a link to these down below so that you can play with them. And right there, maybe that's not big enough. It's big enough. Okay, so here are two objects. There's the red object with two red masses connected by a massless bar, and then the blue also. They have the same mass. So the question is, which one has a greater momentum? And the answer is that if we think about the motion of the center of mass, both of them have the same motion of the center of mass. Both of these systems have the same magnitude of momentum. Even though the red one's rotating, the total momentum is the same because they have the same center of mass motion. Now, what about the energy? Which one has more energy? More kinetic energy. In this case, the red one has a greater kinetic energy. We can think of it two ways. We could say, well, it has a greater kinetic energy because it has a center of mass energy, translational kinetic energy, plus rotational, whereas the blue one only has translational. But you can also think of this in terms of the absolute velocity. So let me show you an example. Let's look at the actual velocity vectors. Okay, I'm going to try to pause this right. That's good. Okay, up here in the blue one, we can calculate the total momentum as this mass times this velocity plus this mass times this velocity. So it's going to have a total momentum in the x direction. Done. Now up here, this one has a momentum in the x direction that's greater, right? Because it's moving faster. It's rotating, and that rotation means that at that point it's moving that way. I always get that backwards. To the right with a greater velocity. So that one's going to have a greater x momentum. However, the bottom mass is actually moving to the left in the negative x direction. So it's going to have a negative x component of momentum. When you add these together, you're going to get the same momentum. So it doesn't matter that it's rotating, they still have the same momentum. Now, what about in terms of kinetic energy? I can do the same thing. This one's going to have 1/2 mv squared, 1/2 mv squared, and that has some kinetic energy. This one's going to have a greater velocity, right? It's greater than that one, so it's going to have a greater kinetic energy than that one, 1/2 mv squared. This one's not going to have negative kinetic energy. It's not going to cancel. It doesn't matter that it's moving to the left because kinetic energy is a scalar. So it's going to have also positive kinetic energy, so you combine those two together and the kinetic energy is greater. Center mass velocities, let's just run that. That doesn't really help. Okay, cool. Now let's look at another program. Let's do this one. And show center mass velocity, show relative velocity. So in this case, I paused it, but you'll notice a couple things are happening. One, the center of mass is moving, so it has translational kinetic energy. It's also rotating. The objects are moving perpendicular direction to the relative vector to the center mass, so it has rotational kinetic energy. And it also has what we'd call vibrational kinetic energy because they're moving towards and away from the thing. And you can only make that work, well, I guess. It's going to have some other type of energy. In this case, there's spring potential energy too, so when it's moving back and forth, it's storing spring potential energy. Okay, let's jump back to the paper. I'm going to show you one more thing on here in a little bit, but I want to go back over to the paper. And I want to show you how we can derive rotational kinetic energy. And my marker feels it's feeling a little not so great, like it needs to be changed. I thought I had a new one, but that's fine. Let's imagine that I have a two-mass object, again, just two masses, and it's rotating. So, and the center mass is stationary. Okay, because I don't want to have to deal with center mass. So I have, here is the center, here's M, here's M. Actually, it doesn't have to be in a line, it's right here. But they are both moving in a circle, in a circular path. So this is M1, and this is V1. I'm just going to write it like that. That's V2, M2. We can first define, and this is the point of rotation, and this is R1, and this is R2, and that's O, my point of rotation. First, we can define the angular velocity omega as based on the time it takes something to make a complete rotation, 2 pi over t, where t is the period. So if I take the time it takes to go all the way around, which is 2 pi radians, divided by the time, I get the angular velocity, and this is in radians per second. I can also find the velocity, right? Because this one's going to have a velocity, let's say it's in a bigger circle. I didn't draw it like that. And it will have a velocity of the distance to go all the way around, which is 2 pi r divided by the time, t, capital T. And you'll notice that that's the same as right there, so I can write this as omega times r. So I can get a relationship, I can describe the motion of this rigid object using these angular velocities. So since both of these are going to have the same angular velocities, but they can have different velocities. And so this is one way to do that. Now that's a scalar, scalar, scalar. There is a vector relationship that you can make for this, but it can get tricky. Once you get, note, I'm going to put it right here. I didn't even write it. Note, fixed axis. We are dealing with objects that spin along a fixed axis. So you can't rotate it in more than one dimension. If you do that, things get quite a bit more complicated. We're not going to do that in this class. You can do that in classical mechanics when you take that. Probably even the second semester of that. It's not trivial. It's not impossible, but it's not trivial. Okay, so now let's write the kinetic energy of this system. So I'm going to call this K rotational because it's only rotating. That's going to be equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. But now I'm going to replace this v's with omega times r. So this is going to be 1/2 m1 omega squared r1 squared. So it's going to be r1 squared omega squared plus 1/2 m2 r2 squared omega squared. Now you'll notice they have the same omega because it's a rigid object. Rigid. So I can actually factor out that. I'm also going to factor out the 1/2. So I can write this as 1/2 parentheses m1 r1 squared plus m2 r2 squared omega squared. And this is all the parameters of that object. And this is just a half, and that's the rotation of it. So I'm in the form that I can write this as I omega squared. And I we call the moment of inertia. And that term doesn't really make sense in this context, but that's what it is. I like actually rotational mass, because that's the rotational or angular velocity. That's the angular mass. And now it looks just like 1/2 mv squared, the kinetic energy term. But in general, my moment of inertia is going to be the sum over I, mi, ri squared. So I'm going to take each mass, I'm going to multiply it by its distance to the axis of rotation squared, and then add that all up. And so I can do it just 2 masses. I could do it for 50,000 masses. It doesn't matter. If I have a continuous distribution, then I have an infinite sum of tiny pieces, and so this becomes an integral. And so it's kind of difficult to write. I'll just write it like this. I equals some volume integral of r squared dm, where dm is the piece, and typically dm is going to be rho times dv, where that's the density. So in Cartesian coordinates, this would be rho dx dy dz for a full volume, but there's a lot of cases where maybe you're just flat. There's a lot of different situations, and honestly this can get a little complicated. It's fun, but it gets a little complicated. Let me just say that in general, if I have a stick like this and I integrate by rotating it around an axis in the middle, then the moment of inertia, and this is the length L and a mass m, it'd be 1/12 ml squared. If I have a stick, and these aren't too terribly difficult to derive, and I rotate it about this axis at the end, it's going to be 1/3 ml squared. And so you'll notice it not just depends on the mass, the size, and the mass distribution, but how that mass is distributed about the axis of rotation. So if you move the axis of rotation, you get a different moment of inertia. A disk about the center, we have I equals 1/2 m r squared, where that's the radius. A sphere about the center, I is 2/5 m r squared. But I wouldn't expect you to memorize those things. I'm just letting you know that these could all have the same mass and same diameter or whatever, but they're going to have different moments of inertia, and that's okay. Okay, we have one more thing. I'm gonna tell you what we're talking about here, and then I'm gonna show you an example. And this is another way to think about the work energy. Remember, work is the change in energy, and the work is we calculate as F dot dr. And then the change in energy depends on the kind of system, but we could have things like kinetic energy, potential energy, and things like that. Thermal energy. Thermal. Okay. So let's consider the following situation. Suppose I have a person, and that person squats down to jump. And then, so that's my person. And then this is position 1. And this is Y1 is the location of that center mass. I didn't say this before, but, and I'm not going to, I'll just say it. The center mass, you can use center mass for the gravitational potential energy too. I didn't write that for you. And then as they jump, they're gonna push up until they get into this position. There's their feet. They're still on the ground, and there's their center mass a bit higher, Y2. And then they're gonna jump in the air, and they're gonna reach some height up here, and we'll call that Y3. If you consider the work energy principle, we can actually look at this in terms of a real and a point particle system. So I'll call this PPS, point particle. And then we have the real. I'll put it over here. We've mostly been using the point particle system so far, but in a point particle system, there's a couple of important points. The work is, I'll write this as F dot delta R CM. We calculate the work based on the change in the center of mass. So if you're going from here to there, the change in center mass is from Y1 to Y2. The change in energy is just kinetic energy. Okay, we can only have kinetic energy in a point particle system. If it's a point, it can only have kinetic energy. In the real system, the work is F dot delta R F. It's how far the force was applied. So over here, imagine that the floor is pushing on the person. In the real system, the floor didn't move. So the point of application didn't move. So in this case, that would be 0 work. In this case, it would be F floor times Y2 minus Y1. It did do work in the point particle system. It did not do work over here. The floor doesn't really do work on the person, right? Now, but also in the real system, the change in energy, we can have all sorts of things. We can have change in kinetic energy plus change in, I'll just call this internal energy. So the person can have a decrease in chemical potential energy, or whatever you want to call it. The person uses their muscles. They have that, right? They can do that. So if it's actually very useful to use both of these systems, right? So if I want to find out things about the change in center mass, I'm definitely going to use the point particle system. If I want to find out things about forces that don't actually do work, I need to use the point particle system too. But if I want to find out things about like the changes in internal energy, then I need to use the real system. And I think it's important to say which system you're using, real or point particle, and to realize that in the real world, when you jump, there is a force pushing up on you, but it doesn't do any work on you. But we can pretend like it does and use it to calculate awesome things. And that's the difference. And it does take some practice to get used to these. Let's look at an example in Python that I think is quite useful. Going back over here. 2 pucks. Okay, here are 2 pucks. They have the same mass, they have the same diameter, and they both have the same force pulling them to the right. The only difference is the top puck has a string wrapped around the outer edge of the puck, and the bottom puck is attached to the center. So let me just run this, and we see. The question I ask my students is, well, which one's going to have a greater, if the forces are applied for 3 seconds, which one's going to have a greater change in momentum? And the answer is same. Right? The answer is same because it's the same force, it's a same time, they have to have the same change in momentum. So let's run that and see what happens. And you'll notice that they are moving side by side. They have the same center of mass velocity. But what's different? What's different is that the top puck is also rotating. That means the top puck has translational kinetic energy and rotational kinetic energy. So how can it have more energy than the bottom puck? And the answer is right here. As this top string is pulled, it's going to move further. So in the real system, this force is applied over a larger distance. So this top force does more work than the work done on the bottom force. That means that the top puck is going to have more energy, even though it has the same translational kinetic energy. Now, if I wanted to use this in the point particle system, I wouldn't care about how far that force is applied. I'd only care about how far the center mass moved. And if I did that, I could find the change in kinetic energy of the center of mass. But I couldn't find anything out about the change in rotational kinetic energy. However, if I didn't have this second puck down here, I could do this problem twice. I could do it with the real system. I'd first do it with the point particle system and find the kinetic energy and velocity of center mass. And then I'd do it with the real system and find the total work done. And I already knew the change in translational kinetic energy, so the leftover stuff has to go into rotation. And that's one of the ways we use this point particle versus real system. But like I said, it takes practice. If you just always say, I'm going to write down my system, I'm going to say what the whether it's point particle or real, then you can go from there. If it's point particle, we're dealing with the change in center of mass for the work. If it's real, we deal with the displacement of the force. That's how you do those. Okay, so that's chapter 9. There's a bunch of stuff in there, but it's awesome.